Hello out there, this is Nicole Hemsoth, editor of HPCwire. We'll be bringing you an interview today on the topic of in-memory computing for scientific applications. One of the reasons why we're tackling this today is there was an announcement from GridGain about a recent project in which they were selected to provide the in-memory computing infrastructure for a Portland State University program that's seeking to tackle some really complex computational chemistry challenges. The larger goal there is to be able to build an adaptive learning system that can detect pathogens, provide diagnostic information, therapeutic information, so that they can eventually have a biocompatible biomolecular computer that can be embedded into an actual living cell or body. Pretty interesting stuff. So as you can imagine, these types of chemical simulations require quite a bit of computational power. And instead of relying on what they had available at the time, Portland State University researchers looked to GridGain and in-memory approaches to solve their problem. So to learn more about that, we are talking today to Jon Webster, GridGain's VP of Product Management. So, Jon, can you give me a sense of your background? What's your title there? What do you do?
Yeah, sure, Nicole. I'm the VP of Product Management here at GridGain. Was actually employee number one in behind the founders here. Been with GridGain for some time now.
Okay. And so are you one of the pioneering people behind the in-memory HPC product?
Yeah, absolutely. That's really the core of our overall product stack. It is kind of the heart of it, if you will, and we do in-memory computing across a couple of different workloads. HPC is obviously the sort of pure parallel computation capabilities, and then we have an in-memory database which embeds that HPC in it, as well as having some streaming workloads around that. But certainly the HPC component is actually one of the oldest pieces, if you will, of our technology stack, very widely deployed around the world.
Okay. You know, it's funny, when I hear in-memory, I don't necessarily think of HPC workloads. In-memory is being bandied about as a term in the big data business analytics space. So for HPC users, where's the value and how does this differentiate compared to what a lot of them are already working with?
So this is a really interesting question. And when you start hearing about in-memory or in-memory computing in general, led by some of the other vendors and some of the things that they're saying, what you largely are talking about, or they're talking about, is storing data in memory, so some subset of data in memory. And for us, that's certainly a necessary component of in-memory computing, but it is not sufficient to handle today's in-memory computing workloads. And by this, I mean, I kind of mentioned a little earlier in our discussion that, we actually embed our compute engines, our HPC capability, the parallel computation, across this large partitioned in-memory database. So if you think of this, you've got all of your data in memory. It's certainly sitting there. And with sort of an old school way of doing things, you go and you reach into your data store. And I mean, this is for RDBMS systems on, disk-based RDBMS. It's for caches. It's for in-memory databases, all of these kinds of things. The data resides there. You reach out, you grab this data, you take it somewhere and you process it, and then you put it back again. And the thing I want you to notice is, of course, that data movement across networks and across machines. So for us, coming back to your question, for us, what we've done is we've taken that HPC component. There are some classes of problems which don't require data, but, to varying degrees, almost all do. And we've embedded that processing capability with the data. And we have a notion of data locality or data affinity, and this is really about in situ analysis, essentially, right, where the data largely resides at rest. So you're really trying to minimize data movement. You can't eliminate it entirely. Of course, you do have to move a little data at some point. But the point is the computation travels out to the data, executes locally. The first law of distributed computing is don't distribute. So it executes locally, and then maybe there'll be a smaller result set returned, or a computational result returned. So that really is where you see the kind of the leveraging of both that traditional HPC parallel execution, be it MPP, SMP, RPC, whatever the kinds of parallel computing you're doing, or MapReduce for that matter, along with that processing plus data. So for us, that's what gets me excited, and that's really what the HPC component brings to the table for us, as opposed to maybe the traditional just pure compute HPC that folks are looking for, which we do perfectly well. But I think it really does get really exciting when you can do the compute plus the data.
Right, right. So let me understand this then. There is an issue then of having kind of hot data that you're making use out of often. I imagine probably very large data sets if you're dealing with some of the scientific workloads that I know that you guys have in the news today. So to what level is that the case, and to what degree is this automated? I mean, what level of complexity is there for the system admin or whoever's managing this?
For us, one of the things that we've done is make this simple. That's really what our customer feedback time and time again, and our research clients that are using this, they essentially say, look, you can, you handle GridGain, all of the hard stuff about parallelization and executing and data in memory and all of those kinds of tricky things. Distributed programming is non-trivial in many respects, right? So that's where we do. So our deployment methodology, our deployment topology rather, and methodology for that matter, very, very simple, very straightforward. You can tie together all sorts of heterogeneous resources if you want to. Very, very straightforward to use, and that's I think one of the benefits. Now, you make an interesting point about data or hot data as well, and it's kind of I've got customers who run into tens of terabytes of in-memory data stores. We've been designed memory-first architecture, meaning my primary data store is expected to be in memory. And I highlight this because it's not just about caching. It's not just about fetching sort of hot data. We transact on data in memory 100%. And, I've got a customer in New York running 15 to 20 terabytes of in-memory data. And that, for them, that's their entire data set. Now, we, of course, do allow you to read through and write through and variously sort of caching schemes and, eviction policies and all of the mechanics of getting the right data in the right place that you might want to see. And I also am not suggesting that disks go away in this kind of infrastructure. You do have disks at some point, whether it be for overflow or long-term durability. But for us, that's really kind of our view of the world on how these things work. We're perfectly happy running fully in memory. I mean, I think some of my customers report back to me, a terabyte across some commodity blades perhaps is, $25 to $28,000 per terabyte. So this is really very quickly kind of democratizing this in-memory computing space for a wide variety of workloads and various types of problem domains.
So I'm sure you've tested this, or at least some of your users have. Where does the scalability wall slam down on you then with this approach?
That's a good question. So for us, we have independent tests and customers running, multiple thousand nodes, 2,000, 3,000, 4,000 node grids out there across sort of more or less the same number of servers, two data centers in the UK and in New York and back and forth across the WAN link. For us, we spend a lot of time being very thoughtful about how we design and architect the system. So for us, you can scale out almost limitless in an almost limitless fashion, and it is very near linear scalability as you add nodes across these. Now, the other thing that I have customers do is I actually can scale up as well. So it's not just about commodity boxes. Sometimes I've got folks that have very powerful boxes and they scale up, and then I've got other customers who scale up and out. So it's really a great mix. From the product, it's certainly not one or the other, and I don't really necessarily have a specific recommendation. It's very much problem-driven. It's very much workload-driven as to what you would want to do. But as I say, we're easily tens of terabytes of data in memory, very easily thousands of nodes and servers of GridGain running in production across our customers in that way. And I guess I'll answer the question this way, is that, we haven't actually bumped up against the kind of the max, if you will, that we've found, because quite simply, for the problem sets we're addressing, you can do astonishing things in several thousand nodes and tens of terabytes of data. It's really quite incredible what my customers are doing.
Right. How is something like this that's sort of nebulous in concept and not tied to one architecture, as it were? How do you price something like this?
Well, so we have a combination. We have a combination of a server unit is what we call a combination of essentially cores plus memory that's bundled into a standard server unit. Is that and as that scales, obviously folks who are doing 100 nodes and folks who are doing 5,000 nodes, there's obviously an inflection point as to how we would discount that as those go as those scale up. But really. Very straightforward, and it's essentially how much compute and how much memory you're using is really how we toll, if you will, the utilization of software.
Okay, that was not clear at all. It's really difficult when you talk about products like this to try to assign some sort of value and ROI. And at the end of the day, that's really what people's questions are around. They can understand the technology, they can put it in context, like you guys did today with your Portland State announcement, which we'll talk about in just a second. It's just difficult to establish a sense of ROI on technologies that the value is kind of floating. So, this approach compared to just running it on somewhat vanilla hardware, working that out, I imagine, would be a tough sell.
Well, I think that what we do is we take a look at essentially, our customers certainly take a look at what the options are for doing this in the absence of GridGain, I think I would say. And for a lot of my customers, they approach net new workloads, net new things they can't do in the absence of that. And, again, our server unit is 4 cores and 16 gigabytes of RAM. And, we just calculate based on what your overall utilization of the software the software is. So maybe it sounds a little more complex than it does, but it's certainly straightforward. There are other options for this, but I think the integration of the products that we have, the ability to scale to the levels that we do, and frankly, the ease of development, the ease of use, and the ease of deployment are not to be underestimated. Our customers are left with integrating 2 or 3 different products themselves, or using the unified stack that GridGain has to bring these capabilities out there. But again, typical enterprise software, I guess I'll say.
Right. So let's take everything we just talked about and put in the context of your announcement today. You guys worked with, you provided the in-memory computing infrastructure for Portland State's computing with biomolecules. So they have an adaptive systems computational chemistry research project. Can you describe that very briefly?
Yeah, sure. So we've been working with the folks at Portland for some time now, and in general, we try and work with almost as many research institutions as we can. We've always been very supportive of university research. We have an academic licensing program that makes this technology available to folks like the folks at Portland State to be able to do these types of things. So, as I understand it, what they're doing is computational chemistry, and this was actually a very interesting use case. And what essentially, a simple explanation of what computational chemistry is they use a simulation of chemical reactions and how things work to actually sort of do a lot of research without actually mixing chemicals. So it's funny, when I was speaking with the folks there, it's like, we do chemistry without the actual chemicals, or we're not pouring things. And the very complex, chemical reactions that they're doing allow them to do some very interesting things. And these are very computationally complex, and they, of course, want to be able to scale up and scale out and do these things in a much more reasonable time. I mean, I think one of the folks was telling me that they're getting things, in hours, minutes, and at worst days that would normally take a year to compute. So essentially, chemistry without the actual chemicals. I have this notion of beakers and measuring things together, but it allows them to accelerate and explore actually more than they could do if they were actually doing it in a traditional lab setting.
Where does in-memory fit into this exact type of research? So I imagine they're comparing different chemical reactions, and they want to store just the elements that they're using in memory, so they have quick access to them. Is that proper way of looking at this then?
Well, it is, yes. So, but again, I'll come back. I'll say that's kind of 50% of the problem. The storing the interim results and the ins and the outs, and keeping that information in memory is certainly important. But they have, in this case, a very complex computational model. And again, the details of that are actually, beyond me, quite frankly. That's, as I say, it's, theoretical chemistry here. But the point being, they have a very complex computational model that they need to actually calculate. So they need raw processing power on a massive scale, in addition to that very low latency data access. So that's really how you look at using these technologies to approach these kinds of problems.
Mm-hmm. So for scientific computing users, what other application classes might be a good fit then?
Well, there's a whole bunch of different folks that I've got, using the software. Everything from biological research, so genetic research, for instance, a lot of interim result sets, searching for polymorphisms, which essentially are just things that are different across very large genomic data sets. Real-time sequencing. I've got a lot of material science that's done, so a lot of calculations on, a very, very basic example would be, where things break, essentially, in computational models on bridge building, for instance, and things like that. I've also got a number of folks doing things with seismic analysis, so looking for fault lines and analyzing earthquake data, analyzing, things for the oil and gas industry in an academic context, although also in a commercial context for that one. So it's a very wide variety of different kinds of problem sets. Essentially what you're looking for is a computational model. So you've got to compute something. You have a challenge that requires that raw mass processing power. You've got a data component that's coming at you, either streaming at you, or is a relatively large data set, and can benefit from low latency access across that.
Mm-hmm. So the last question I have then, all of those application areas you just mentioned are exactly the types of applications that people talk about GPUs being a great fit for, or coprocessors. Do you want to comment on that?
Yeah, so for us, we are much more, I guess I'd say generic, as opposed to the specializations of the GPUs. The GPUs are very, very good technology for cranking math, essentially. For us, we actually are a little bit more general purpose, if you will. So very, very straightforward APIs, very, very straightforward Java APIs. Essentially, if you know how to use Java and a hash map, you know how to use our technology and can distribute to 1,000 nodes. We don't have any specific plans for any GPU enablement right today. It is something that some of our customers are looking at for. But, even in the case of Portland, they looked at some GPU-based stuff, but the ease of use and the scale and the ability to very quickly get to where they needed to be ultimately won out. And really, honestly, it's why they're looking and are using us today. Originally looked at us and are using us today.
Mm-hmm. Okay, great. Well, this is a really interesting use case, and we'll be exploring a little bit more in the written section of this. Thank you so much for your time, and we'll look forward to more news coming from you over the course of the year.
Well, Nicole, thank you so much for your time today. It was great to speak with you, and lots of exciting news from us, lots of exciting science getting done on our stuff, too. So I will look forward to the opportunity to talk to you again.
Excellent. Have a good day.
Thanks. Bye-bye.
I'm still here. It's
Okay,
tempting to hang up.